Back at the tail end of the 19th century, physicists pretty much thought they had it all figured out. Light was a wave, end of story. But then, this tiny little spark, just a simple observation, was about to blow that whole picture wide open and reveal a secret, particle-like face of light that would literally change the world forever.
So where does our story begin? Not with some grand sweeping theory, but with a really strange and persistent mystery that physicists just couldn't sweep under the rug.
On the surface, it sounds incredibly simple, right? Back in 1887, Heinrich Hertz noticed that if you shine ultraviolet light on a piece of metal, it helps sparks jump across a gap. Basically, photo, for light, was creating electricity. The little electrons that got kicked out were called photoelectrons. But buried in this simple effect was a puzzle that was anything but.
Well, because when scientists really looked closely at what was happening, it broke all the rules. At least, all the rules of 19th century physics. It kicked off this huge crisis that was going to take nothing short of a revolution to solve. So, to really get why this was such a game changer, we have to look at what everyone thought should happen, and then compare that to what was actually going on. Okay, so back then, everyone agreed light is a continuous wave. Just picture ocean waves hitting a beach, right? It's a great analogy. A bigger, more intense wave, a brighter light should carry more energy. So it should give the electrons a bigger kick, sending them flying out with more energy. And even a tiny, gentle wave, a dim light, if you just wait long enough, it should build up enough energy to eventually push a pebble off the shore. It just made sense that any color of light, if you made it bright enough or just left it on long enough, should eventually knock an electron loose. Seems logical, doesn't it?
Well, it was wrong on every single point. The experiments showed something completely different. The energy of the electrons had nothing to do with the brightness of the light. It was all about the light's color, its frequency. And if the light's frequency was below a certain threshold, nothing happened. 0 electrons. It didn't matter how blindingly bright the light was. And when they did pop out, it was immediate, instantaneous. There was no waiting around for energy to build up. The classical wave picture wasn't just a little bit off, but completely and totally backwards.
Now, this didn't all just happen overnight. This was basically a 15-year-long detective story, with different scientists finding these strange clues and slowly building a case that classical physics just couldn't solve. It all kicks off with Hertz's first observation in '87. A year later, Holox confirms that whatever is being spit out of the metal is negatively charged. But the real smoking gun, the critical blow, comes in 1902 from Philipp Lenard. He did these incredibly careful experiments, and he proved, without a doubt, that if you double the brightness of the light, you double the number of electrons that fly off, but their maximum energy, it stays exactly the same. That energy was tied only to the frequency of the light.
So by 1905, you've got this mountain of evidence, but still no explanation. And then along comes this 26-year-old patent clerk in Bern, Switzerland, a guy named Albert Einstein, who proposed an idea so out there, so radical, that people just thought it was reckless.
Einstein basically said, hey, what if we've got it all wrong? What if light isn't this smooth, continuous way at all? What if it's more like a stream of tiny, individual packets of energy? He called them light quanta, but today we know them as photons. So it's not a gentle wave washing over the metal. It's a hailstorm of tiny energy bullets. And here's the kicker. Each one of those bullets, or photons, has a very specific amount of energy, and it's determined by this beautifully simple formula. E for energy equals h, which is a fundamental number called Planck's constant, times nu, the frequency of the light. So higher frequency light, like blue or UV light, just means you've got higher energy bullets. And that led him to his full photoelectric equation, which just perfectly explains the whole mystery. Honestly, the easiest way to think about it is like a vending machine. The photon's energy, that h nu, that's the money you put in. The work function, that's the price of the snack. It's the minimum energy it costs to free an electron from the metal. And your change, the leftover energy that the electron flies away with, that's Kmax. Now, if your coin, h nu, is worth less than the price, phi, you get nothing. It doesn't matter if you put in 1,000 coins that are too small. This is exactly why there's a threshold frequency. It's why the electron's energy depends on the color of the light, not the brightness. The whole puzzle just snaps together.
So it's a beautiful theory, right? It explains everything perfectly, but for most physicists at the time, this idea of light particles, it was just absurd. I mean, it completely contradicted 100 years of experiments showing light was a wave. It needed rock-solid proof.
And one of the biggest skeptics out there was this absolutely brilliant American experimentalist named Robert Millikan. He called Einstein's idea reckless, he thought it was totally wrong, and he decided he was going to be the one to prove it. I mean, this guy spent a whole decade working on this. He built this incredibly precise apparatus, figuring out how to scrape the metal surfaces perfectly clean while they were inside a vacuum tube. His one goal was to run the most perfect, most definitive experiment on the photoelectric effect ever performed, and to finally put a nail in the coffin of Einstein's bizarre theory.
And then, you get the ultimate plot twist in the history of science. After 10 years of trying to tear Einstein's idea down, Millikan's own data ended up being the most perfect confirmation of the theory you could possibly imagine. When he plotted the electron's energy versus the light's frequency, he didn't get some complicated curve. He got a perfect, straight line, exactly what Einstein's equation said he should get. And the slope of that line? It was Planck's constant, h.
And the number he got for h? It was insanely accurate. We're talking within 0.5% of the value other people had found from totally different experiments on blackbody radiation. The man who set out to kill the theory became its ultimate validator. The proof was just undeniable.
I mean, this whole saga was so fundamental to physics, it ended up netting 2 Nobel Prizes. One went to the theorist, Einstein, who dared to come up with the reckless idea, and the other went to the experimentalist, Millikan, who, in his quest to prove it wrong, ended up proving it was absolutely right.
So you might be thinking, okay, that's a cool story from history, but why does it matter today? Well, it turns out this discovery, Einstein's idea about light's particle nature, is the foundation for countless technologies that you and I use every single day.
Every single time you see a solar panel soaking up the sun and making electricity, you're looking at the photoelectric effect in action. The sensors inside your digital camera or your phone that capture light to make a picture, that's the same thing. Those automatic doors at the grocery store, streetlights that turn on by themselves, even super advanced scientific tools that can analyze what materials are made of, they all depend on this quantum leap that Einstein made more than a century ago. So what this all comes down to is that the photoelectric effect proved that light has this secret identity. We all thought it was a wave, but surprise, it's also a particle. It can be both. And this shocking discovery of wave-particle duality, well, it didn't just stop with light. It kicked open a door to a whole new way of looking at reality itself, and it forced us to ask a really profound question. If light can lead a double life, what else out there in the quantum universe has a secret identity?